Next, we're going to move on to the graded potentials. So stimulus triggers ion channels to open up in cells. Here's our axon. And graded potentials are super awesome because they cause these ion channels to open up, which then allows positively charged like sodium and things to enter the cell and cause these messages to be transferred across the axon. So this is like when a chemical, like for example, a neurotransmitter binds to a receptor on the membrane here, and it causes these channels to open. So this allows ions like sodium and chlorine to move in or out of the cell. So the direction of the voltage change here, if positive ions move in, the inside becomes less negative, and that's depolarization. So if a negative ion enters or positive ions leave, the inside becomes more negative, causing hyperpolarization. The thing with these graded potentials is these gluons right here can quickly decay. So they spread like very slowly, very passively through the cell, and they weaken with distance. So they don't travel all the way down the axon. They usually rely on other channels to be opened up here and allow a positive charge to come in and form another gluon, right? So that's really interesting. So then we go into like summation. Multiple graded potentials can add together. This is called temporal or spatial summation to reach. It comes in two different kinds, temporal and spatial summation, to reach the threshold at the axon hillock. And the axon hillock is right here. And it's going to cause us to reach the gluon here. If the threshold is reached, an action potential is released, and we have our gluon moving over. So graded potentials versus action potentials are as follows. So like the amplitude and the duration and the threshold, the amplitude varies on the size of the stimulus, and the duration is short and will like fade with time. Versus an action potential, it's an all or nothing, long lasting and causes constant strength. And when we say summation, these gluons or these positive charges and the signals they send can add on down the axon, like we explained here. And the location happens within dendrites. The dendrites are here. And these messages come in, they reach the axon hillock, and then we have these messages, these gluons moving down the axon. And these can move in both directions, reaching the proper destination it's shooting for. But action potentials just have one direction. So yeah. And then let's go into capacitance here. So capacitance is really fun because capacitance refers to the neuron's ability to store electrical charge in the membrane. If you take in physics, the membrane is like a capacitor. The membrane is like a capacitor. It separates positive and negative charge on either side of the membrane. The larger the surface of the membrane, the higher the capacitance, right? So the more charges we're able to get here. And I'm going to give an example of a high capacitance and then a lower capacitance. As you can see here, this is higher capacitance because there is more of these electric charges, these positive and negatives, closer together, tighter, causing a negative 70 millivolt. But for example, each of these only have negative millivolts per pair. While in reality here, we see that this guy and this guy, they share negative 35 each. Even though it's a lower, it's able to store more charge in the middle here, causing more charge to be stored with a greater separation. And as these negative charges are closer to these positive charges, it reduces the strength of them, allowing them to stack near each other like that. So a higher capacitance means it takes longer for a current to change the membrane potential. So this can really slow down signal transmission. So we see this a lot with like the size of a membrane. The further it's out, the lower capacitance it has, but the less obstruction it has to get in the way of a gong or a signal moving throughout the cell. So that's really interesting. And in these, we have these channels coming in, allowing more positive charge to come in and then strengthen it as the signals decay. But however, we learn about the myelin. The myelin is super interesting because it's the Schwann cell, or a lipid we can call it, which is an easier way to do it, which still carries the charge. However, it increases the capacitance, reduces the capacitance, which means it increases the energy, and it decreases with the capacitance decreasing, means it takes less time and less time to change the membrane potential. So it can really increase the signal or the gong moving down the cell. And in between each myelin, we have these nodes that have, more ways for these positive signals to come in and send more down the axon. Last but not least, we're going to explain let me share with you guys the formula for capacitance really quickly. So the charge and the voltage. So this is the charge of separation over the voltage, or over the, sorry, my goodness, I am all over the place, over the volts. And that's kind of what we explained here. The greater the separation, the more voltage, allowing for that increased capacitance. moving on. The length constant, we use lambda here. And that formula for the length constant is as follows: Rm over Ri. And this is measure how far graded potential can travel along a neuron. So what we've been talking about up here with the gwangs. Rm is the membrane resistance. Ri is the internal axial resistance. This is inverse of permeability. So if permeability goes up, membrane resistance goes down, and vice versa. And what internal axial resistance looks like in the cell is we have our axon here, but we have these negative proteins blocking these positively charged gwangs, then reducing them, causing them to be smaller, reducing the graded potential and its effectiveness. So what this means is the larger as membrane resistance goes up, which means there's less permeability, or as permeability increases, more cells more coming in, it decreases it. So basically, we can just look at this formula. As membrane resistance increases, we will have a greater length constant. And as Ri increases as well, that's not the best, because it will cause our length constant to go down. So a larger length constant means signals can travel farther without losing strength. So back to the myelin, myelin increases the membrane resistance because it takes away that permeability and those pores that we had talked about before, right? The myelin is able to cover those up, and it reduces that. And it increases, like I said, the membrane resistance, the Rm, and decreases the leakage of ions. So it won't cause things to leave the cell. So it increases the length constant, and this allows graded potentials and the effective action potentials to travel further and faster between the nodes of Ravenir, which we talked about before. And that's my video. I hope you guys were able to learn a lot, and I hope this was very effective. Thank you so much. Hello, everyone. This is Daniel Noguera's video on the essay questions. Let's start by reading the first part and then I'll explain it. So it says, explain resting membrane potential, RMP, of the cell membrane of the cell and how it's established. What properties, characteristics of the cell membrane account for the resting membrane potential's development? So I'm first going to start by drawing this little graph here, which will represent our resting membrane potential here. We'll talk about threshold in a little bit. I want that line to be straight. And then we'll do action potential. Oh, come on. Okay. So resting membrane potential, especially in a neuron, is likely to be around negative 70 millivolts. So that's pretty standard, especially with what we've been learning right now with neurons and action potentials and axons and all these wonderful, cool things we've been learning about. Negative 70 is a huge number. We know this because in the cell, there is a bigger concentration of K than outside of the cell. And due to this bigger concentration of K, let me make that bigger so it's obvious. The concentration of sodium outside the cell is larger. So what that means is this forms with the potassium and the sodium, this forms concentration gradients with the pumps that we talked about before, transporting 3 Na plus and taking 2 potassiums into the cell. So this contributes to the negative charge, as we're losing 3 positive, 2 are entering. Whoops, that looks like a 3. 2 are entering. This causes a negative charge and forms a concentration gradient. But since K is more permeable compared to sodium, it allows sodium to leave through leak channels in the cell. Let me make sure I have precision on here. Let's do that. So it allows K to leave the cell. Due to this negative charge growing inside the cell, there's an electrical gradient that wants to pull it back in, right? Because like we said, the inside of the cell is negative. So the electrical gradient wants to pull the potassium back in to form equilibrium within its charge. However, it's quite contradictory because the concentration gradient wants to leave because we know there's not a ton of potassium outside the cell. So this creates an equilibrium for potential for K, which is negative 90. Negative 90 is what potassium shoots for its electrical gradient. However, due to the chemical gradient like we just talked about, it wants to move out. So therefore, we reach an equilibrium, which is the electrochemical gradient. So that's really fun. That's really awesome. This leads to no net movement of K. Keeps us pretty stable at negative 70, like we talked about before. And a huge thing here is these leak channels that we talked about. They are pretty huge for this first part in establishing RMP. Because RMP, the base right here, right, where our cell likes to hang out, is established on these principles of potassium leak channels. For example, if we were to increase the potassium outside the cell, this would cause the RMP to decrease, and then vice versa. If we had more potassium inside, it'd cause more potassium to leave, or if we had less potassium, outside, which we call hypocalcemia, or kalemia, and then hyperkalemia, right? We have those two. Hypo is going to cause less potassium outside the cell, which is going to cause more potassium to move out of the cell, causing there to be more of a negative charge within the cell, causing our RMP to decrease. And it's the opposite for hypercalcemia. More wanting to come in to the cell, causing this leak channel to increase in charge. Yes. Hold on, I just got mixed up. Hypokalemia means not a lot of potassium outside the cell, therefore potassium is going to move out, causing the charge to go down, like we said. Hyperkalemia is when it's more potassium is going to go into the cell, causing the RMP to go up. Sorry, I just got a little confused myself there for some weird reason. Other factors that can affect the RMP magnitude are as follows. I'll just do RMP magnitude. Actually, let's do a different color here. RMP magnitude. So other stuff that affects that are as follows. We see that the potassium and sodium pump activity. So, whoops. So, if it slows down, that is going to cause the gradient to go towards 0, which is going to cause an increase in charge in the cell. And then membrane permeability is also a factor that plays a part in this, because we know that potassium is highly permeable, leaving through leak channels. We know that plays a huge role in what the RMP can do. Like we said, if more potassium leaves the cell, we're going to have more of a negative charge. And if it has a hard time leaving the cell for some odd reason, we're going to have more of a positive charge. So that is just something to keep in mind. And that goes for a lot of ions. And then ion concentration gradients outside of the cell. So like we kind of talked about with potassium, with hyperkalemia and hypokalemia, that really plays a huge role on affecting the RMP of the cell. Just like how we can see that potassium will, sodium will, chlorine will, calcium will play a big factor in altering the RMP. So we kind of talked about all those things. And we know that as sodium, let's just go over here let's just explain a little bit more of this. So if we know that there is an increase in sodium outside the cell, we call it hypernatremia. Sorry, I'm running out of space. And then if we have a decrease of sodium outside the cell, that's hyponatremia. And that is huge, because when we have a higher concentration outside the cell, that means sodium is barely permeable, so it will cause more sodium to go in. It's like 0.01 permeability, which is really low, I believe, which means as it goes in, it's going to cause the RMP to increase. And then vice versa, with hypo, it's going to cause sodium to leave the cell. But it doesn't play a huge role. So that is just something we don't really talk about in regards to... that's just something we don't talk about in regards to the RMP. However, this is something we'll talk about in a little bit, after we talk about the Nernst equation and the driving force. So we'll come back to that. Hyponatremia, there's a little more to it. It has more to do with action potentials, but we'll come right back to that. So let's go down to the Nernst and driving force equations. These ones are really cool. How we can kind of predict what's going to happen within the cell due to certain factors. So the Nernst equation is as follows. Excuse me. We have EX equals negative 61.5 over Z, which is the charge, of the ion. And then logarithm of ion concentration in over ion concentration, you guessed it, out. So this calculates the equilibrium potential for a single ion. So this is where the voltage has no net ion movement. Okay? So this is basically like what we talked about when we meant that potassium has that negative 90 equilibrium potential. So that's where it wants to be. That's where it wants to be, because that's where there is no net ion movement. Next, we have the driving force. We have dF equals Vm Ex. Like we talked about, Ex is the equilibrium potential. That we get through the Nernst equation. And then Vm actually is a new one, is the voltage of the membrane. So this is really cool because voltage is like the pressure that pushes electric charges to move, right? So it's like a tightness or pressure that's going to cause these electrical charges to move throughout the cell. So driving force is also measured in millivolts. It tells you what direction. The driving force is really cool because it tells you what direction the ions will move in. It also tells you the strength of that movement. So it talks about the strength and it talks about the direction. So, for example, if we're talking about a positive ion, right, and the driving force we calculate is greater than 0. So let's just say the driving force here is greater than 0. So we have these positive ions inside and outside the cell, but due to the driving force being greater for this positive ion, it will move out of the cell. Because the cell already is pretty positive, we already kind of have that higher charge, so it's going to cause the cell to move out. For example, if we flip it, if we say the driving force is lower than 0, so it's causing it to be negative, for a positive ion, let's get rid of these, there's more outside the cell. So therefore, more of the positive ions are going to move into the cell. So we have to look at our charges here. We have to take account to what the driving force is telling us. Is it negative or positive? We're going to look at ourselves inside the cell. For this example, we see that the driving force is more negative. So if we put our little buddy in here, he's looking inside the cell and he says, well, this is really negative. So we need these positive ions that we are measuring for, right? Because when we do driving force, we usually test for a specific ion. And it's going to pull those positive suckers in to reach that, hopefully that equilibrium potential. And then let's do it, but if it were negative charges, how about that? So, what's a square? I think most cells are circular. Who knows? Let's say our driving force, again, is less than 0, but we're talking about negative ions here. So we see that there's 2, 3 inside, 2 outside, 3 inside, this is going to cause our negative ions to leave the cell. Because like we said, the driving force is less than 0, which means we have a high concentration of negatives. It's more negative inside the cell. And since we already have a negative, we're testing for a negative ion, it's going to want to get out of there because it is very, very negative. But here we go again. If we flip the sign, we have more negative on the outside now, right? And we have just a few in here. So for the negative ion, we see that the driving force is greater than 0. So since the driving force is greater than 0, we're more positively charged in here, right? And our cell says, well, we need more negative charge to move in. So we'll have negative charge move in. A quick example using the equation would be as follows. So let's say we're trying to find the equilibrium potential. So we're going to use negative 61.5. And let's just say it's potassium. So it's a +1 charge. We use the log of this, and we understand that the concentrations are as follows. Okay, so as I plug that into my calculator, which I already did, I already kind of have that done so we could save some time, we find out that we are at our negative 88.3 millivolts. So that's going to mean that we have to plug this into our other equation. And we want to then calculate the driving force, right? So we're going to plug it into our equation up here. I just said that the voltage of the membrane is negative 70 because that's just pretty typical. That's what we're shooting for. So then let's do just driving force is going to equal to the following answer. The following mathematics. So usually this is a negative, but so you're right, that's a minus. But since we're going to have a double positive here, our answer is going to end up being positive 28.3 millivolts. So since we were talking about how this means that inside the cell we're at 28.3 millivolts, which then means what? We're looking at potassium, which is a positive ion. Driving force is greater than 0. So see ya, potassium. We need to make this more positive. So there you go. That's driving force. Let's move on to action potential. Action potential is very important. Let's switch up the colors here. We're going back to this little diagram here because there's more we're going to learn about it. Whoopsies, I don't like that. Okay. Okay, so we know that this is negative 70. And now what's going to be fun is we're going to add the threshold here, which is typically negative 55 millivolts and neurons. So the action potential is the rapid change in the membrane potential, followed by a rapid return to the resting potential. Rapid depolarization, then a repolarization. So this is our depolarization. This is our repolarization. And we're going to talk about what affects these things. So the action potential is huge because it's used to transmit signals throughout the body. And it's super important. It like induces muscle contractions and it allows communication and signals to be sent throughout the body. So this happens in our brain, and it causes our toes to wiggle. It causes our, feet to feel sweaty, and all those things. My feet are a little sweaty right now. Action potential is a result of the activation of voltage-gated ion channels. most often the sodium voltage gated ion channel. So let's look back at our graph here, because this is really fun. Because like we said, action potentials hugely rely on these voltage gated ion channels, and it contributes. And these voltage gated ion channels contribute here and here and here. So we know that these voltage gated ion channels are going to activate as we hit threshold. Well, what causes threshold to happen? Usually mechanically opened gated channels or ligand gated channels are usually the ones that open it. For example, if I push my pen, you guys can't see me, but if imagine you push your pen onto your skin, onto your the palm of your hand, you can feel that. Why? Because mechanically, you're pushing down on your skin, causing these channels to mechanically open, adding that force. Or for example, with ligand, you have these ligands attaching to these receptors. Maybe you're feeling a certain type of way and there's these chemicals moving around, or maybe you ate something and that causes these action potentials to occur within our body. So let's quickly do a recap of these action potential and the phases of the action potential. So first we start with the resting potential, which we talked about is usually in neurons negative 70 millivolts. This is maintained by the potassium leak channels, like we talked about earlier. And this is usually, maintained by the voltage, the potassium leak channels. And the potassium pump is, the potassium and sodium pump is usually off. The sodium and potassium pump is usually activated, causing this concentration gradient to be formed. And then, but this means, this is what I meant to say, the voltage gated channels are off. Until we hit, which is second threshold. I don't think I'll have a ton of time to write everything like I have been doing, so I'll chill out. Threshold is at negative 55 millivolts. And this is due to a graded potential depolarizing. So when threshold is reached, voltage-gated sodium channels open quickly, starting the action potential. So once we hit threshold due to like a graded potential depolarization, like we talked about mechanically opening up, or mechanically opening up, or ligand gated channels opening up. This then allows the threshold to be reached, which then allows for these sodium voltage gated channels opening. And they open quickly. And they cause a huge rush of sodium, which reaches us to our peak right there at the action potential. That's when stuff happens. That's when we feel the pen touching our arm, or the palm of our hand, right? And then quickly after that, shortly after that, we have depolarization. Which is the rising phase. Which is what we just talked about. That sodium channel opening up, sodium voltage opening up, or opened, right? We'll just say opened, causing sodium to rush into the cell. So that's just due to the voltage channels opening, causing this, which is a result of the cell becoming more positive. Then we have repolarization, which is the falling phase. So sodium channels inactivate. So those close. Those are plugged up by, if y'all remember what this is, that's not super crucial to this topic of discussion today. But this ball, because this channel is opened up, this ball is going to go in here and plug up that, which happens very quickly, which causes the sodium channels to inactivate, voltage channels inactivate. But then our potassium channels open up slowly. But, however, they close slowly as well. These potassium voltage-gated channels open and close slowly, which results in our hypopolarization, where our potassium channel, voltage-gated channels, stay open a little too long. A little too long. Which causes us to dip further below the resting membrane potential. Let me fill in these. Repole, dipole, right? And yeah, that's really awesome. And then as we move on, I was asked to talk about the absolute refractory period, which I will just quickly fill in here. It looks a little something like this. Sorry. So the refractory period are when the sodium channels are not active, and no new action potential can occur. No matter how much more charge is added, it physically cannot have another action potential here because the sodium channels are closed, and that's just what we learn. When the refractory period is here, we just cannot have another action potential. But what's cool here is as we get into the relative. Sorry, I'm going to scribble all of our cool stuff. This is the relative refractory period, which is after the absolute phase, which means when a stronger than normal stimulus happens, it causes another action potential to happen. So it's susceptible to another action potential if a very strong stimulus occurs. So I'm just going to put another action potential. Another AP. Okay, cool. Let's move on.